Welcome everybody. Let's start our class. I hope that all of you joined the meeting. Start the recording of it. Okay, so today's class will focus on some guidelines for your self-assessment test that you got last Friday. And then we will see some tools that could be very useful when dealing with the experimental structural dynamics. So let's see your self-assessment test. I'm going to publish it at the and therefore share with you the file. I didn't have time this weekend to do that, but I'm going to do that by today or tomorrow. So don't worry about that. I will share this text with you. The first question, so question number 1, was dealing with measuring chain that is composed by a potentiometer and cathodic ray tube that is very useful to check your quantity, your physical quantity, just by reading that on a screen. Okay, we didn't deal with that for sure. Okay, but I gave you the sensitivity of such a cathodic ray tube in order to make some discussion with that. So your overall measuring chain, that is your measuring chain, okay, we receive as input your whatever unknown displacement xi that could be measured by your potentiometer, and the output of that will be the displacement d, okay, that is the deflection of the on the screen of the electronic beam. Okay, and in order to assess that, I'll give you the equation in the text. Okay, So we have to put the things together. Now, if you remember the potentiometer, okay, we'll have, just focusing now on the potentiometer, was characterized by a circuit. Remember, we have, for example, like that. We have your overall resistance, the potentiometer. This is your input voltage to the circuit, and then the overall resistance is Rp. Then by using a mechanical device, we can have information of whatever displacement, okay, xi with a reference, okay, with respect to the overall maximum that could be measured. Because of that, we can measure the output tension, but in order to measure that, what we need is a measuring device, and then we have to introduce an additional resistance. Okay, in order to have your whatever output tension. This output tension was called E output. And if you remember, we had that the overall relation between your output and your input tension is given you by this very annoying relation xi over xt, remember, plus rp over m 1 negative xi over xt. Okay, and we had a lot of discussion about this equation. Okay, but however, if the rp over rm ratio is going to 0, that is, the resistance of your measuring device is much higher than the potentiometer internal resistance, then that relation could be simplified a lot, okay? Because what we can say is that the output, sorry, with respect to the input voltage here, okay, is equal to simply xt over, sorry, xi over xt over xi. Okay, and that's what we are having there. So that we can see that your E0 over xc, sorry, I made a mistake. Okay, E is equal to di over x. Okay, made a mistake over here. I'm very sorry. Okay, E x. That's it. Okay, so in order to, and that is the first block of your measuring chain. Then we have to consider the second block. The second block is the cathetometer, sorry, the cathodic ray tube, cathodic ray tube, sorry. And we didn't see anything else. Size with an input tension Vf that is capable to excite your electron somehow over there. This is your electron. This electron is passing through some acceleration plates. Okay, those acceleration plates are characterized by a distance h, okay, and a length that I call L, lower L, like that. Okay, Because of that, by your output E0, that is related to the displacement that we want to measure. And then finally, your electron is shift like this, and then it's going straight to your screen. And what we can measure is this distance t when the screen is located to the distance L. Okay, and I'll give you the relation. Your d is equal to 1/2 L over h, that are the acceleration plates properties. Then we are having the E0, that is your tension that is exciting your acceleration plates with respect to the tension that is required to excite the electron to exit from your whatever material, and then the length L. Okay, so what we are having is that the overall sensitivity, the distance with respect to your input displacement, is given you by this ratio. Okay, so the sensitivity that could have the deflection d with respect to the input tension EO times EO over xi. Everything is in place. D over E0 could be obtained from the previous equation. So what we got is 1/2 L over H L over Bf. And then in the under the hypothesis that the potentiometer resistance is much less than the measuring device resistance, then that is equal to E over, oh sorry, xt. And that is your answer. Okay, so let me rewrite that. E over xt is equal to 1/2 L over H L over Bf times Vi over xt. So discussion about this sensitivity. In order to increase that, please remember that your input tension at the potentiometer stage should be not that much to melt everything. So we have to consider the maximum dissipable power that we can have in the potentiometer circuit. Okay, then what we like to have is xt that is going to a minimum. You have to reduce the scale if you want. Then L over H should be maximized, so you have to go back to your general device and therefore try to have L over H the maximum possible. Okay, and finally we have to increase the F to a maximum value, but again we can't melt everything, but we don't have any other information for that, so we can say just that. And the screen should be at the right as much the right position, that is L should be the farther possible. Okay, I don't know, I didn't see any one of you that was doing that, maybe because you don't have the right time, but please remember that everything in the measuring chain should be put one over the other and then work as I did. Okay, try to find out the sensitivity, the overall sensitivity that could be obtained by considering each block of your measuring chain that receive an input from the previous block, and it is producing an output for the next block. Okay, so that you can have the overall sensitivity. Then question number 2. Do you have questions about this? Hmm? Okay, so question number 2 was referring to the static tests. Okay, so in order to answer that, just remember we are considering 3 tests: limit, load, factor tests. Then we are ready the ultimate, load, factor tests, and then finally the failure tests. Okay. Just to discuss what can we do with the limit load factor test, what I should have written there, just some comments concerning the fact that these are useful for checking or assessment of the elastic behavior. Okay, behavior. Please also to know that we have to check for possible free plays. What about the ultimate load factor test? In these, for this test, we are checking the elastoplastic behavior. Okay, and therefore some damage failure in some components. Okay, and we have to ask where and for how long there is no failure of such a component, and it should be greater than 20 seconds. Okay, and we have to check that so that we can say that your numerical model is good enough to predict some ultimate loads, that is your material properties and components are correctly modeled. Okay, and that is of course very, very important. Finally, the failure tests. Here we have to break everything, we have to know that, and we have to identify what are those loads that are setting the structure into the failure condition. Everything was broken. Okay. Questions? Question number 3. Question number 3, we have to consider the effects of temperature, okay, in the measuring, while measuring the strain using the resistance-based strain gauges. Okay, what are these effects? Remember, we have to start from the very beginning, so we have to say that the relative change of the resistance is given you by this very well-known formula, in which K is the strain gauge factor, epsilon is the strain, and the delta R of R are the change of the resistance and the base resistance respectively. So what we have to discuss is that your delta R over R is a function of the change of temperature, that your K also is a function of the temperature, and that your Third, also your strain depends on the temperature. Okay. And so you have to discuss these three effects. We already discussed them. And maybe you can end up with the compensating plot, sorry. So in which we have the T, in which we have the apparent strain. Okay. Something like that. We have to characterize what's the meaning of T0 and then show possible plots like this, for example. Okay, in which for a given temperature we have an apparent strain, so that the overall strain is given you by the strain that has been measured by, for example, Wheaton bridge configuration, and then we have to take out this apparent strain corresponding to the operating temperature. Okay, finally, the last question. Was asking you how is working a piezoelectric based accelerometer. Then we have to just remark that there is the piezoelectric effect. Okay, so PCT effect. You remember the PCT effect is telling me that if I have a sort of